This is lesson 3.5, first row D block elements. So in the D block, or the transition metals, the first row does not show the same periodic properties as the rest of the periodic table. However, they do have similar physical and chemical properties within the transition metals themselves. So here's some very important uses for transition metals. Iron has the alloy steel, and copper is used in wiring. So they're two very important metals that we use all the time. And in terms of their electron configuration, the atomic radii for transition metals are really similar because there's only a small increase in effective nuclear charge. Because remember, those 4s electrons are the valence electrons. And first of all, they're really far away. And second of all, they have almost the same amount of shielding. So the effective nuclear charge really remains pretty much the same across the transition metals. So the electrons that are added for each successive transition metal are being added to an inner orbital, a 3d orbital. And they also have a smaller range in ionization energy because of this similar effective nuclear charge. Please remember that chromium and copper are exceptions to the electron configuration, and go back and review them if you don't remember what that exception is. An alloy, remember, is a mixture of metals. Think back to our gold penny lab. And the reason that transition metals can form alloys are because of that sea of electrons. So the d electrons in metals can exchange to bond together and form alloys. So when you mix transition metals together, their d electrons are actually interchanging so that they're bonding them together. So transition metals have high electrical and thermal conductivity. They have high melting points. They're malleable. They have high tensile strength, meaning that they can hold up very large loads. They're ductile. And remember, they all have metallic bonding, which is that sea of electrons which holds the metal lattice together. In terms of chemical properties, the transition metals are similar in that they all have more than one oxidation number. They form a variety of those complex ions that we're going to talk more about. They form highly colored compounds, and we use them a lot as catalysts. Now, here's where we lie to you. Scandium and zinc are not transition metals. They do not form colored solutions, and they only have one oxidation state. So when we write the electron configurations of the scandium ions and the zinc ions, it's very easy to see why they're not the same as other transition metal ions. For example, scandium has the electron configuration when it loses 3 electrons, 1s2, 2s2, 2p6, 3s2, 3p6. And zinc has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. And we can see that these ions are going to be different from other transition metal ions because scandium, when it forms an ion, loses its d electrons. And zinc, when it forms an ion, has a full d subshell. This is very different than the other transition metal ions because the other transition metal ions all contain some electrons in the d orbitals, and the d orbitals are not full. So why do transition metals have more than one oxidation state? First of all, you must memorize some of these oxidation states. So to help you memorize them, here's a few tips. All transition metals have +2 and +3 oxidation states. The maximum oxidation state increases in steps of +1 and reaches the maximum at manganese as you go across period 3. The 4s and 3d electrons are used in bonding, and after you get to manganese, the maximum oxidation state decreases in steps of -1. Oxidation states above +3 are generally covalent in character when the transition metals bond. And compounds with higher oxidation states tend to be oxidizing agents, which means they like to gain electrons. Alright, let's talk more about transition metal complex ions. So let's talk about ligands. Ligands always have at least one atom with a lone pair of electrons. And transition metals like to form complex ions because they have a high charge, meaning +2, +3, +4, but they're very, very small, so they can attract those lone pairs on ligands. And the coordination number refers to the number of ligands that are attached to that transition metal. So it's the number of dative bonds that are formed. So here, for example, if we have a metal with 6 ligands attached to it, that's an octahedral shape, and it has a coordination number of 6. Here we have a tetrahedral shape. We have a metal with 4 ligands, so the coordination number would be 4. In linear, the coordination number would be 2. And here's just an example that shows, depending on the transition metal and the number of ligands and the type of ligand, you get all these beautiful colors. So for example, scandium, remember, and zinc we said are not transition metals and they are colorless. But look at all these other transition metals that form these awesome colors in solution. And you can see that they all contain a different number of d electrons. So here we have scandium with no d electrons. Here we have zinc with a full d subshell. But all these partially d-filled subshells all have beautiful colors. So why do transition metals appear colored? Well, transition metals only absorb some of the colors of visible light. So for example, here we have iron hexahydrate. And iron hexahydrate appears yellow. And the reason that it appears yellow is because it absorbs blue light. So if you look, it appears yellow because it absorbs its complementary color, which is this blue color. So when transition metals absorb colored light, what happens is the electrons actually jump between the 3D energy levels. So the color that is absorbed is the color that allows its electrons to jump between the energy levels, and all the other colors are what are reflected or transmitted. So color depends on a few things. It depends on the nuclear charge, or which transition metal is in the center, the charge density of the ligand, where the electrons are dispersed, the number of d electrons present and the oxidation number of the central atom, and the shape of the complex ion. So here's an example. So this is what your d orbitals look like. However, we lied to you. And the d orbitals actually Okay, so here's what the d orbitals look like, or actually what you have been led to believe they look like. And now we're going to let you in on a little secret, and that is that the d orbitals actually are not all the same energy. So they actually, 3 of the d orbitals are a little bit lower in energy, and 2 of the d orbitals are a little bit higher in energy. So what happens is that when you have a transition metal with an electrons or electrons in the d orbitals, when they absorb energy, they actually jump up to the higher level d orbitals, and then they can also fall back down. And so those transition metals that are colors and create colored solutions are the ones that have d electrons that can jump up and down, whereas scandium with no d electrons in its ions and zinc with a full d subshells cannot have those d electrons jumping up and down because their orbitals are either empty or completely full. So remember, what is a catalyst? So if you think back to biology, remember a catalyst speeds up a chemical reaction by lowering its activation energy. So transition metals are used a lot as catalysts. The first type of catalyst is called a heterogeneous catalyst, and that is when the catalyst is in a different state. Remember, hetero means not the same from the reactants. So the catalyst might be a solid, the reactants might be a liquid. And the reason why this works is because when you have a transition metal that's a solid, it forms very weak bonds with molecules. So for example, here's an example of where we have a reaction right here with the reactants going to products, and this is how much energy it would take. It has to go over this hill, oh, what a tall roller coaster, with no catalyst. However, if we put a transition metal catalyst in there, what happens is these molecules will bind very weakly to the transition metal catalyst, and that transition metal catalyst actually brings them closer together so that they are able to perform this reaction with a much lower hill to get over, much less energy, and then the transition metal catalyst can easily release the product to float away. For example, iron is used to synthesize ammonia, which is used in fertilizer. Nickel is used to convert alkenes to alkanes, which you'll learn about later in topic 10. Palladium and platinum are both used in the catalytic converters in your car. And manganese dioxide, which can be used in the decomposition of hydrogen peroxide. Vanadium oxide is used in the contact process to make sulfur trioxide and sulfuric acid, which is the #1 most used chemical in industry, so that's very, very important. The other type of catalysts are called homogeneous catalysts. And to use homogeneous catalysts, to use transition metals as homogeneous catalysts, you need the ions of transition metals. And homogeneous catalyst means that it is in the same state, homo, as the reactants. So they're either all solids, all liquids, all gases. And homogeneous catalysts are very useful in redox reactions, which we'll learn about in topic 9. But some places where homogeneous catalysts are used are the iron ion in hemoglobin, which transfers oxygen throughout your body, and cobalt ions, which are used in vitamin B to produce red blood cells and keep your nervous system healthy. So, last we just have this short little video on hemoglobin.
Red cells are particularly well suited to transporting oxygen because they contain a special oxygen-binding protein known as hemoglobin. Each molecule of hemoglobin itself contains 4 molecules of heme, an iron-containing pigment, which binds oxygen loosely and reversibly. Hemoglobin that is fully saturated with oxygen is bright red and is called oxyhemoglobin. On the other hand, hemoglobin that is not saturated with oxygen is purplish blue in color and is called deoxyhemoglobin. It is heme which makes it possible for the red cells to pick up oxygen dissolved in the blood, transport it combined with hemoglobin, and release it back into the blood as oxygen in solution, ready for delivery to the various cells of the body. Hemoglobin gives up its oxygen as red cells travel through capillaries in tissues where there is a low content or partial pressure.